All right, so our next objective is to convert between sigma notation and other notation for a series. So given a sequence a sub n, and the sequence is a list a1, a2, a3, the sum of the sequence of terms a1 plus a2 plus a3 plus dot 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 on forever is called an infinite series. Well, adding up an infinite number of things is going to be a bit of a challenge, and we'll talk about that. We'll also talk about, well, first of all, does it make sense to add up an infinite number of things? And if it does, what does it represent? But that'll be a question we'll answer a little bit later. So let's start with a slightly simpler question, which is a partial sum, which is the sum of the first n terms of a sequence. And this will always exist. So the symbol s sub n says add up the first n terms of a sequence. So s sub 5 would say add up a1 plus a2 plus a3 plus a4 plus a5. All right, let's go ahead and look at a concrete example. So we wish to find s1, s2, and s3 if a sub n equals 2 to the n. So s sub 1 says add up the first member of the sequence, so there's not really anything to add because that's only one sequence member, which is then 2 to the first power, which is going to be 2. S sub 2 would ask us to add up a1 plus a2. Well, a1 is going to be 2 to the first power, plus a2 is going to be 2 to the second power, so that's 2 plus 4, which is going to give us 6. And s sub 3 would be a1 plus a2 plus a3, which is 2 to the 1 plus 2 squared plus 2 cubed, so that's 2 plus 4 plus 8, which is equal to 14. So it's worth noting that the partial sums, or the SNs, make a new sequence. That is, so 2, 6, 14, 30, dot, dot, dot. So that is the sequence of partial sums. So the next thing we want to talk about is sigma notation. So sigma is a letter of the Greek alphabet, and we're actually going to be using capital sigma. And capital sigma looks kind of like a capital E. And the Greek letter capital sigma tells us to add up all of the numbers of a sequence. So in this notation, down here at the bottom, we have what is called our index. And the index tells us what sequence member to start at. So this tells us what sequence member to start at. So in this case, it's telling us to start with the third sequence member. The number on top tells us where to stop. So what sequence member to stop at. And so this tells us to stop at the seventh member of the sequence. And then the a sub n tells us the general term of the sequence, or this is our rule. So this is the general term of a sequence. So the symbol is read as the following. So we have the sum as n goes from 3 to 7 of a sub n. So in our sigma notation, we read this as the sum, so the sigma symbol is read as sum, as n goes, the index where we start, from 3 to 7, our stopping value of our sequence. So to make this example a little bit more explicit, the sum as n goes from 3 to 7 of a sub n would be, we start at a sub 3, so it would be a sub 3 plus a sub 4 plus a sub 5 plus a sub 6 plus a sub 7, and we would stop at a sub 7. Alright, let's look at example number 8. So we wish to find this sum. So remember, sigma tells us to add. So this is asking us to add up the sum as n goes from 3 to 5 of n squared. So when n is 3, we get 3 squared plus 4 squared plus 5 squared. And we stop at 5, so then we get 9 plus 16 plus 25. So that sum is going to equal the number 50. All right, it's your turn. So go ahead and find the sum as j goes from 5 to 7 of 1 over j. So this is going to be 1 over 5 plus 1 over 6 plus 1 over 7. So since 5 and 7 are prime and 6 factors into only 2 and 3, all of these numbers are relatively prime. So then our LCD is going to be the product of all of these. So the first one's missing a 6 and a 7. This is missing a 5 and a 7 in the middle, and a 5 and a 7, and the last one is missing a 5 and a 6, and a 5 and a 6 for our common denominator. So then adding those up, 5 times 6 is 30, and 30 times 7 is 210. So 1 times 6 times 7 is 42, plus 1 times 5 times 7 is 35, plus 1 times 5 times 6 is 30. So then adding 42 plus 35 plus 30 gives us 107 over 210. So the sum as j goes from 5 to 7 of 1 over j is 107 over 210. So in the interest of full disclosure, our graphing device can do these sums as well. So let's go ahead and turn on our calculator. So to get to our summation, we are going to press our alpha key, and then we are going to press window. So we go alpha and window, and we look at choice number 2, and we see the Greek letter sigma. And if we type in this example exactly how it looks, so j is the alpha function on our comma, and j goes from 5 to 7, and then we press alpha y equals to get our fraction, and we do 1 over alpha comma to get our j, and we think for a moment, and our calculator gives us the same value that we just got, adding it up manually. So we can use our graphing device to sum up a series in sigma notation. So to use our graphing calculator, we need to know the starting value, the stopping value, and the general term of our sequence. Alright, so let's put all of that together in example number 9. So we wish to find the sum of 3, 6, 9, plus dot, 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 all the way out to 333 plus 336. So we need to write this in sigma notation. So we need to find the associated sequence. So our sequence, a sub n, would be 3, 6, 9, 12, all the way out to 336. So what are we doing each time to get to the next sequence member? Well, we are going to add 3, add 3. So we know the general term of our sequence, a sub n, is going to be 3 times n. So now we need to find the index for both the starting and stopping terms. So all right, so we take our starting term, we need to solve a sub n equals the first term, which is 3, and our stopping occurs when we make it to the last term. We need to solve a sub n equals 336. So a sub n is 3n, so that gives us the equation 3n equals 3. Divide by 3, divide by 3, and we get n is equal to 1. And our second equation is 3n equals 336, so we divide by 3, and we get n equals 112. So finally, in sigma notation, we're going to have the sum as n goes from 1 to 112 of 3n. So alpha window, we grab choice number 2, and we have n goes from 1 to 112 of 3 times n. And press enter, and we get that the sum is 18,984. All right, let's take a look at our last example. So we want to talk about a recursively defined sequence. So a sequence is recursively defined when it is defined in terms of its previous sequence members. So in this example, we have our seeds, which are A1 and A2. And we have that our general term is defined now in terms of these sequence members. So when we write a sub n equals a sub n minus 1 plus a sub n minus 2, the first thing we want to take note of is that this n minus 1 and n minus 2, the subtraction is in the subscript. So when we say a sub n minus 1, this is the term before a sub n. And a sub n minus 2 is the term before a sub n minus 1. And we mean that in the list. So then, when we have n equals to 3, we want to find the third term of the sequence. Well, a sub 3 is going to equal to, if this subtraction is in the subscript, 3 minus 1 gives me 2. It's equal to a sub 2 plus 3 minus 2 is 1, a sub 1. Well, what is a sub 2? Well, a sub 2 was given as a seed, and it's going to be 1, and a sub 1 was also given as a seed, and it's going to be 1 as well. So then this is equal to 1 plus 1, which gives us 2. All right, so now to get our next sequence member, we would use n equals 4, and that's going to give us a sub 4 is equal to a sub 3 plus a sub 2. Well, now I need to know what a sub 3 is, but a sub 3 was what we found in the previous step. So we know that the value of a sub 3 is 2 plus the value of a sub 2. Well, a sub 2 was one of our seeds that was given originally, and we know its value is 1, so 2 plus 1 gives us 3. Going to our next sequence member, when n equals 5, we get a sub 5 is equal to a sub 4 plus a sub 3. And once again, we need to know what a sub 4 is, but luckily, a sub 4 was what was found in the previous step. And we know that the value of a sub 4 is 3 plus a sub 3 was found 2 steps ago, so that's going to be 2. And so finally, a sub 5 is equal to 3 plus 2, which is 5. So we notice, as we said, that this sequence depends on the sequence members that came before. So if we write this out, we had a sub 1 was 1, a sub 2 was 1, a sub 3 is 2, a sub 4 is 3, and a sub 5 is 5. And we'll notice that we could have gotten the next sequence member by going 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5. So our next sequence member would be 3 plus 5 is 8. And the next one after that is 5 plus 8 is 13, 21, and so forth. And this comes from, when we look at our rule here, it says a sub n is equal to the term that came before it, and then the term that came before that, which was